Okay.
Good afternoon, everyone. My name is Jinfei Wang, and I come from Yat-sen University in China. It's a great pleasure for me to share our recent progresses here. I'm going to talk about the impacts of combined ENSO and SAM on the Antarctic sea ice budget. Here, sea ice budget represents a simple distinction between dynamic and thermodynamic contributions on sea ice changes. As we all know, Antarctic sea ice plays an important role in the polar climate system. In contrast to the rapid decline of the Arctic sea ice extent in the context of global warming, as this yellow line shows, Antarctic sea ice displays a complex trend since 1978, as the green line shows, with a record high in 2014 after long-term increases, and then dropping to a record low in 2017 and this year. Therefore, the significance of the long-term trend is low due to large year-to-year fluctuations. Current climate models have difficulties simulating the trend precisely. This figure shows the linear trends of autumn Antarctic sea ice concentration. The left panel is derived from satellite observations, and the right panel is CIMIP-6 simulations. We can see that models from CIMIP-6 obtain negative Antarctic sea ice trends, which are inconsistent with the observed trend, which has significant regional differences. This requires us to investigate a better understanding of the driving mechanisms behind. The interannual variability of Antarctic sea ice is linked with large-scale climate modes like the Southern Annular Mode, the Nio Southern Oscillation, wave number 3 pattern, and semi-annual oscillation. Among them, SAM and ENSO are the primary drivers of sea ice variability. This figure shows the correlations of SAM index and sea ice extent, and the correlations of ENSO index and sea ice at different longitudes. It can be seen that SAM and ENSO have similar impacts on sea ice, but with opposite sign, especially in the Indian Ocean and Pacific Ocean. Additionally, previous studies have found that the impact of ENSO on atmospheric circulation of southern hemisphere depends on the phase of SAM. This article indicates that only during in-phase conditions, which is when a La Nina is concurrent with a positive SAM or an El Nino is concurrent with a negative SAM, the impact of ENSO is enhanced and is significant. However, we wonder how the combined impact of SAM and ENSO on sea ice is. To answer this question, we analyze the seasonal Antarctic sea ice responses under each combined situation and their regionally dynamic and thermodynamic contributions. The sea ice budget equation used in our work is suggested by Holland and Kwok. Partial C partial T is called sea ice intensification and is calculated by a central difference between sea ice concentration from the day after and before. The second term is the dynamic contributions, including advection and divergence processes, calculated by sea ice concentration and sea ice motion data. The residual term is considered as thermodynamic contributions according to previous studies, but also with a little bit mechanical redistribution. We apply composite analysis to examine the seasonal fields for each SAM-ENSO combination, and the distinguished circumstances based on detrended and standardized SAM and ENSO index are shown in this figure. Here shows the differences of composite anomalies between two in-phase conditions, which is La Nina with positive SAM and El Niño with negative SAM. Each row is a related variable, and each column is a season. We can see that for in-phase condition, there are significant seasonal variations for all the anomalies. The sea level pressure presents a marked low pressure in the eastern Pacific sector, which deepens the Amundsen Sea low. These local anomalies grow stronger from summer to winter, and then become weaker in spring. Induced by the sea level pressure anomalies, 10-meter winds present intensified westerly winds and cyclonic winds around the low pressure, resulting in a distinct temperature dipole. Sea surface temperature anomalies also display a dipole, but do not totally correspond to the air temperature fields. Consequently, sea ice concentration anomalies present a dipole under the influences of both atmospheric and oceanic processes, with negative anomalies in the Bellingshausen-Weddell Sea and positive ones in the Amundsen Western Ross Sea. Comparing the results of combined events with single events, take La Niña positive SAM as an example. We find that sea ice anomalies of combined events do not resemble a linear sum of the single events, which might indicate a nonlinear response of sea ice to some ENSO signals. Then we investigate the in-phase sea ice budget. Each row is a budget component, and each column is a season. We add the net surface heat flux to explain the thermodynamic contributions. The in-phase sea ice intensification anomaly in summer is dominated by thermodynamic processes. In autumn and winter, intensifications grow larger and display a dipole between Atlantic Ocean and Eastern Pacific Ocean. Dynamic processes, including divergence and advection, cause a similar magnitude of contributions as thermodynamic processes. In spring, inner pack sea ice flows outside in the Weddell Sea and Ross Sea divergently and melts at the ice edge, inducing more melting in warmer ocean. Compared with in-phase conditions, the anomalies are apparently different in the out-of-phase conditions. The consistent positive sea level pressure anomalies cover the whole Antarctic without showing any distinct centers. The air temperature anomaly dipoles disappear. The sea ice concentration anomalies present no dipole patterns, but are basically consistent with temperature anomalies, showing opposite anomalies between Weddell-Ross Sea and Bellingshausen Sea. For the out-of-phase sea ice budget, dynamic effects play a more important role in summer. In autumn and winter, more negative intensification happen, and the dynamic anomalies are caused by convergence and advection induced by westward drift, associated with the thermodynamic effects shown in net surface heat flux. Spring intensifications show generally opposite patterns to in-phase conditions. Net surface heat flux are weaker than in-phase conditions. Here is the summary of our research. First, in-phase events are characterized with a sea ice concentration anomaly dipole between Weddell-Bellingshausen seas and Amundsen-Ross seas, which disappears in out-of-phase events. Besides, sea ice concentration anomalies do not resemble the linear sums of those during ENSO-only and SAM-only events, indicating a complex nonlinear response of Antarctic climate to SAM ENSO signals. Through the budget analysis, we find that anomalous thermodynamic processes dominate in summer, while anomalous dynamic processes control the sea ice changes in other seasons. That's all for my talk. Thank you.